Hello, good evening. I hope I'm audible. Can Ananta, can you just put in the chat or unmute yourself and say if I'm audible? So, good evening and welcome to today's class. I don't know, probably it's because I kept the class a bit early. I'm not sure how many of them can join. Uh, However, we'll go ahead with the classes. The video will be available in the eGuru portal. So, I believe those of them who couldn't attend the class can access it to that. Okay, so moving on, the last class, uh, we we discussed about um, the C3 photosynthesis exclusively. What are the reactions happening during C3 photosynthesis? Then um, and we talked about ACI curve, AQ curve, AT curve, brushed up through those basics, and also we introduced ourselves to this model called Farquhar-von Kammerer-Berry model, or in short form, we can call it as FVCB models. So today we'll go more deeply into these FVCB models. I think I'll wait for 2 more minutes because a couple of them have uh, joined, so I'll just wait for 2 more minutes. So those of you who are here until now, have you been are you able to follow it? I mean, I'm not sure which all back. Anamta, what background are you from? And can you just put it in the chat box and if you're able to follow the content that is taken during these classes? Krishna also. Okay, so I believe all the theory part, and are you, Anant, are you familiar with these models or is this new to you? Okay, so today we'll go through this model in detail and how we can model as in it is nothing but a bunch of equations. And when there are equations, there are independent variables and dependent variables. So there are some terms in which when you put it as an input, you will get a certain output. So we are going to familiarize ourselves with what are these terms and how these terms are helping us find out the output. What is the output? And how can we get these inputs? I mean, even for the input, we need to have a certain set of values with us. I'm also having bottom, okay. Okay, thank you. So we have to be able to figure out how to where to get these inputs from and how to measure these inputs from. And if we put the input, what are the outputs we are going to get? All of these are things that we need to figure out. So today we'll go more into details of this FVCB model. So last class, yeah, this is just a refresh, just to refresh your memory regarding the last class. We talked about what are the three photosynthetic response curves. Photosynthetic response curve is nothing but giving us the response of photosynthesis to different different parameters or variables or factors. And the three major factors that we are giving importance over here is the intercellular carbon dioxide concentration, light intensity or light absorbed by the plant, and temperature of the leaf. Now in ACI curve, we saw that there are three phases for ACI curve. The first phase of the sloping phase that is determined by the action or the activity of rubisco that will help in carboxylation reaction. Then the second phase, which is a slightly less slope portion, that is transition from the sloping portion to the asymptote, is giving us an idea about how fast the RUBP is being regenerated. And the final phase is giving us an idea about the TPU limitation, or how triose phosphate utilization will impact the rate of photosynthesis. And then in AQ curve, we are also similar to ACI curve. From AQ curve also, we are getting a bunch of important information. One, I told the quantum yield, which is nothing but the slope. The slope, you can see that as the light keeps increasing, carbon dioxide uptake keeps increasing. So if you see till one portion, it is a linear curve. So what is the slope of that linear portion of the curve? And you can see if you draw a line like this, if you draw a line from this point and extend it like this, what is this slope or what is that angle will give us uh, the slope of this, that is this of this line, the slope of this straight line, which is depicting how this linear portion of the curve is going, is the quantum yield. Then we have the light compensation point, which is the point at which the net carbon dioxide uptake is zero, because there is no intake. The respiration and the photosynthetic rate is reaching a zero. Then there is this intensity of light, which above which the photosynthetic rate is not going to increase, and we have the dark respiration rate obtained from this AQ curve. Then, yeah, I talked about how the variation of the slope can give us information regarding how well the plant, which is represented by these curves, will how efficiently they utilize light for the uptake of carbon dioxide. In a similar way, AT curve is nothing but as the temperature increases until a particular point, uh, the photosynthetic rate will keep increasing. But beyond that point, which is called the optimal temperature, photosynthetic rate will start decreasing. So it is also important that, I mean, this is relevant in case of the in the future climate conditions. Although we can imagine that the temperature is going to rise very in a drastic manner by the end of the century. So if the temperature that these leaves are exposed to is really high, what happens to the photosynthetic rate? Will it start decreasing? Are some things that we can study using this information. So now let's again go in detail. I think I started with the Rubisco limited photosynthesis, but I would like to repeat it because this is something that requires a lot of familiarizing with if it has to stay in your system. So the Farquhar von Cameron and Berry model, it is a biochemical model that is giving us the rate of carbon dioxide assimilation in C3 plants. Now, what this model does is, it is using the ACI curve to help in obtaining the Rubisco limited the photosynthetic rate in the Rubisco limited part of the ACI curve, the RUBP regeneration limited phase, or the photosynthesis during the RUBP regenerated limited phase from the ACI curve, and what is the photosynthesis during the triose phosphate utilization phase. Now, many of you might have a doubt regarding how do we get a particular value of photosynthesis from this curves. So we see that if you look at this curve over here, uh, this portion is not just giving us one particular value of photosynthesis. Here, for this value, for every value of carbon dioxide, we are getting a particular uh, particular value of photosynthesis. So what we are going to estimate is, if suppose we have a point over here, or a photosynthetic rate that is correspond, say this is around 5. So if we have a photosynthetic rate of 5, by solving this set of equation, we can understand that whether this an equal to 5 comes in this portion or this portion or this portion by uh, analyzing this curve or by fitting that data to this curve. So finally, if we get one curve that is representative of the photosynthesis of a plant, if we have the net photosynthesis value, we know that this net photosynthesis value is affected by the Rubisco part. So with increasing carbon dioxide, Rubisco is the one that is mainly controlling the photosynthetic rate over there. Now suppose we get this value of the particular value here, say 25 uh, is the photosynthetic rate. Then we know that from this curve, it is since it is in this portion of the ACI curve, we know that this photos at this level of photosynthesis, the plant is being impacted by light. That is how fast RUBP is being regenerated or how slow RUBP is being regenerated, which is a function of light. Because electron transport is what is giving us energy, what is giving this part, this RUBP the energy for RUBP regeneration. So how fast the electron transport or how slow is the electron transport, as a result of which this RUBP regeneration is being impacted, is what we can understand from this value of the net photosynthesis. And similarly, if you get this value of photosynthesis, we know that at this phase, it is impacted by TPU rate. So if we have this corresponding value, we know that photosynthesis is being controlled by the triose phosphate utilization at this level of at this level of net photosynthesis. So from the curve, we can get all of these information. Now, in the first Farquhar or FVC, according to the FVCB model, they say that the net photosynthesis. Now, suppose you want one particular value of the photosynthesis. We want to say that at a particular point, we are getting this net photosynthesis, means we have to first calculate the Rubisco limited photosynthetic rate, the RUBP regeneration limited photosynthetic rate, the TPU limited photosynthetic rate. We also need the dark respiration rate, and by this equation we can know that if you say, suppose AC is equal to, AC is nothing but Rubisco limited photosynthetic rate is equal to 25. We get AJ as 5 or say 15 and AP as say 10 and RD is equal to 5. We know that minimum of all these three values is 10. So 10 minus 5, 5 micromoles per meter square per second is what is the net photosynthetic rate of the plant or that point. So this is what that equation is uh, telling us. Now, how do we calculate all these values? How do we calculate AC? How do we calculate AJ? How do we calculate AP? And also RD. From where do we get all these RD values? Now, suppose for ease of understanding, say we have the RD value. We have an AQ curve with this and we know the RD value. In that case, how do we calculate AC? So for calculating AC, we have this formula. The Rubisco limited photosynthesis is given by this formula, where AC is the rate of Rubisco limited photosynthesis. VC max is a parameter that is giving us the maximum carboxylation rate of Rubisco. That is, how fast is Rubisco able to make the carboxylation reaction happen? What is the rate of reaction, that to the maximum rate of reaction as a result of Rubisco is what VC max is. CI, we know it is intercellular carbon dioxide concentration. Now there is this term called gamma star, which is called the carbon dioxide compensation point. I'll explain what that is. Here we have a CI, we know what it is. Kc value is something called the Michaelis-Menten constant for carbon dioxide. Here we have O. O is the oxygen concentration inside the leaf, and Ko is the Michaelis-Menten constant for oxygen. So now, suppose we have the VC max value. Say we did some kind of measurement and we need the input. So for estimating this net photosynthesis, we need the value of VC max. We need the value of intercellular carbon dioxide. We need gamma star. We need Kc, oxygen, K naught. All of these value we need it. Now, oxygen, we know that in the atmosphere, oxygen is around 210 uh, 210 mole fraction. So we know that oxygen, we know what is the oxygen concentration. Sorry, yeah, I forgot about the unit, but we know about oxygen concentration. Now, VC max is some input that we need to know by measuring. So we have some mechanisms to measure the value of VC max. So we have the value of VC max, we have the value of O. CI is also something that we can measure. For now, let's say that we have this value of CI. So using some instrument, we measure the value of VC max, we measure the value of CI, we have the oxygen concentration. Now, how do we calculate the remaining terms? Is what we look at now. Now, these terms marked in red are the ones that we need to find out. And there are separate equations to find that out. Now, this carbon dioxide compensation point, what is it? Carbon dioxide compensation point is nothing but in the ACI curve also, you will find that the curve doesn't start exactly at zero. It starts at somewhere, it starts at a negative value, which indicates that there is some kind of net carbon dioxide uh, that is removed from the system, which we all know is because of photorespiration. So in C3 plants, photorespiration is high as compared to C4 plants. We know there is a mechanism to override this photorespiration. So we have the photorespiration rate over here. So carbon dioxide compensation point is nothing but the point during which the net carbon dioxide, carbon dioxide compensation point is nothing but the time at which the net carbon dioxide intake and outtake is zero. So this value we can get, where can we get this value from? We can get from the ACI curve. So say we don't have this value for from the ACI curve. We have to estimate it. If we have to estimate it, then we can estimate this as a function of the temperature of the leaf. Now I said using an equipment, we were able to. I think every one of you are familiar with the gas exchange, infrared gas exchange analyzer. For those of you who are not familiar with that, I'll be coming to that part in the later. But say as of now, using that machine or using that equipment, we were able to measure VC max, we were able to measure CI. We have to have an idea about this value. So either we can measure this value, we can find an ACI curve and we can get this value. Say if we don't have this information relating to this carbon dioxide compensation point, we can estimate this as a function of the temperature of the leaf. And temperature of the leaf is again something that we can measure. So we got the carbon dioxide compensation point as this is called an Arrhenius exponential. So this is a function of the leaf temperature. So you will use this exponential function, divide this factor by the molar constant, which is in this unit, with the leaf temperature in the unit of Kelvin to get the carbon dioxide compensation point. Okay. Now the next parameter or variable over here is Kc and K naught. I said Kc and K naught are Michaelis-Menten constants. So this Michaelis-Menten kinetics is a parameter that is giving us an idea about the enzyme kinetics in a substrate. So here the enzyme that is playing the role is the rubisco. So How does Rubisco represent itself depending on the concentration of the substrate, which is carbon dioxide concentration inside the leaf? What is the carbon dioxide concentration inside the leaf? Based on that, what is the rate of the activity of Rubisco is obtained from this Michaelis-Menten constant. So this is based on the theory by Michaelis-Menten's enzyme kinetics. In that, what they say is, if the substrate is intercellular carbon dioxide concentration, the substrate concentration at which Rubisco operates at half its maximum carboxylation rate will give us the Michaelis-Menten constant. So say if we have a particular concentration at which the maximum carb, say if we have the VC max is 15, and the carbon dioxide concentration at which the Rubisco can carbon dioxide concentration at which the rate of carboxylation is equal to 7.5. If the maximum carboxylation rate, which is VC max, is equal to 15, a particular carbon dioxide concentration can help in achieving around 7.5 micromoles of carbon dioxide per meter square per second of carboxylation. Then that is what we called as the Michaelis-Menten constant for carbon dioxide. The same thing is there for oxygen also. So the theory behind this is that what is the substrate concentration that is resulting in half of the maximum reaction rate by that enzyme is what is called is given by the Michaelis-Menten constant. So here we see Michaelis-Menten constant in this is representing the affinity for the enzyme Rubisco to carbon dioxide. Now it is only at a particular level of carbon dioxide concentration that Rubisco will be able to conduct the carboxylation. Say if the oxygen concentration is higher than the carbon dioxide concentration, then Rubisco is going to go to oxygen for conducting the oxygenation. So this constant is representing that in the equation. We know it theoretically, but how do we incorporate that theory into this equation is done by this Michaelis constant, where it is giving us it is representing the affinity of Rubisco for carbon dioxide. And this can be obtained again by this Arrhenius exponential equation, again as a function of temperature. So here what a higher value of Kc means is that it has lower affinity. I mean, the Rubisco has lower affinity for carbon dioxide. So it means we need more carbon dioxide inside for this carboxylation reaction to take place. So a higher Kc means that the chances of photorespiration to occur is more. In the same time, if the Kc value is low, it is indicating that Rubisco can function efficiently. So there is no problem for Rubisco to conduct the carboxylation rate. So again, this is a factor that is of very much important in the Rubisco limiting phase. So from the value of Kc and K0, we can understand that if Rubisco can conduct the carboxylation rate efficiently or not, or it is if it is the oxygenation that is happening, can be understood from the values of Michaelis-Menten constant. The same way Michaelis-Menten constant for oxygen also has, again based on the same theory. Here the values 38.05, 79.53 becomes 20.3 and 36.38. Again, this is estimated as a function of temperature only. Here also it is giving us the affinity of Rubisco for oxygen. So there, if we find this ratio of K0 by Kc, that is the Michaelis-Menten ratio for oxygen and carbon dioxide, it will give us an idea about the computations or the how the carboxylation oxygen reaction is happening, which is occurring more or which is occurring less, is something that we can understand from this Michaelis-Menten constants. So again, higher K0 means the Rubisco has less affinity for oxygen, so carboxylation is happening happily over there. But again, a lower K0 means the photorespiration, that is higher affinity of Rubisco for oxygen. So the likelihood of photorespiration to occur is very high. This is again going to reduce the photosynthetic efficiency. So we learned about all the parameters that comes in the Rubisco limited photosynthesis. Again, once again, VC max is the maximum carboxylation rate that is happening as a result of the Rubisco enzyme. You can see the unit. It is how many micromoles of carbon dioxide per meter square per second is uh, is being fixed. That is how in what is the rate of fixation of carbon dioxide. Not only just any rate, but the maximum rate at which carbon dioxide is being fixed is given by this parameter. Now, like I said, this parameter is something that we can measure from ACI curves. ACI curves are measured using an equipment called equipment that works on the principle of infrared gas exchange analysis. We can measure VC max. So say we have the value of VC max, we have CI. So when we measure ACI curve, we have the value of CI also. So we have the CI value. All of these constants can be estimated using the following equations that I just now showed as a function of temperature. So if you measure the temperature of the leaf, you can get this Michaelis-Menten constants as well as the carbon dioxide compensation point of that particular leaf. So does anyone have, sorry, ma'am. Okay, does anyone have any doubt regarding this portion? If not, I will continue to the next limiting phase. Okay, so I don't think anyone has any doubt. If anyone has any doubt, do post it. I have attached a Google form in the WhatsApp group. I think I have shared the link via email also. So if you have any doubts, again after going through the classes, you can ask me through that Google form. That will be helpful for me in organizing and responding in an organized manner instead of just randomly asking in the WhatsApp group. Okay, moving on. Next are limited phases. So we found out the what is the how to estimate the photosynthetic rate in the Rumisco limited phase of the photosynthesis. Now next let's see how we can estimate the photosynthetic rate during the RUBP regeneration limited phase. Now RUBP regeneration limited photosynthesis is also called the electron transport limited rate of photosynthesis. Represented by AJ, we see in this also they have a lot of parameters or variables. The first parameter we see is the parameter called J. J is nothing but the rate of electron transport. You might want to pay attention. J means it is the rate of electron transport, not the maximum rate. It is just the rate of electron transport. Say we also have a method to, okay, we don't have a method to measure that. We have a method to measure CI. We know how to calculate gamma star. We know again CI over here, gamma star over here. Now, apart from J, which is the rate of electron transport, what you see here is there are two more terms called EC and E naught. EC is nothing but what is the number of electrons that are used for carboxylation and what is the number of electrons that is used for oxygenation. So when we consider net photosynthesis, we can never consider just what is being taken up. We should also include how much of carbon dioxide is released out because of photorespiration. So that is why you see in all of the equation, the photosynthesis process and the photorespiration process are equally or equivalently they are represented in all of the equation. So in a similar way, what you see in this equation for estimating the electron transport limited rate of photosynthesis is we have the rate of electron transport similar to VC max over there, which is giving us the maximum rate of carboxylation. Here we have the rate of electron transport. So let's go into what this rate of electron transport is. Now, if you see here, this equation over here is giving us what is the rate of electron transport. It is estimated as a function of Q2. Q2 is nothing but related to light, how much of light is being absorbed. Then J max T is again the maximum rate of electron transport. Now, this value over here is something that we can measure again using that machine that I was saying. So this value we have. So if we have this value, how do we estimate the remaining values is something that we will go through. So you should look here in the earlier in the main equation, we had the VC max value from the main equation. But here we don't have the value in the main equation. Instead, this J value is being estimated using another equation. Now, this equation is called the non-rectangular hyperbolic equation. And in this equation, you can see that this J value, that is the rate of electron transport. Now you can physically relate it to the light dependent reaction, the reaction. The electron transport is occurring. So what is the rate at which electron transport is occurring is what is given by this equation, and this is a non-rectangular hyperbolic equation. And this term called Q2. Q2 indicates what is the maximum fraction of incident quanta that can be used in the electron transport. So again, this is indicating that this equation is dependent on light. So when the light is incident on the leaf, what is the fraction of photons that is effectively used for electron transport is given by this term Q2. J max is nothing but the maximum rate of electron transport. And here theta PS2 is nothing but it is a convexivity term for electron transport rates. Now, let me show you this. Now, please bring your focus to this AQ curve in the right corner. So if you see this, I told about how there is a straight line over here. You see this line is a straight line. So if you extend this line like this, you get what is the slope of this line. Now, when you see from this point onwards, we see that from this point onwards, this straight line is being converted into a curved line. So what is the convexivity factor that is determining this curve is what is given by this theta PS2. So it is a convexivity term for electron transport rate. Now this is also one value that we can measure or we can estimate. But as of now, let us, for ease of understanding, because again, as we go further, things get a little bit complicated. So theta PS2 is a convexity term that we have for now. We have measured that value. So Q2, Jmax is also something that we have measured from using that instrument. Now what we have to estimate is Q2. Now Q2, we don't know what is the light that is being incident and how much of those photons are being taken up by the plant. So in order to estimate that, we have this equation. Q2 is equal to I into phi PS2 into beta PS2 into 1 minus lambda R. So what are all of these terms? Let's go into that. So Q2 is equal to I into something. I is nothing but the incident light on the plant. So now we were talking about what is a fraction of light that is being used. So when the light totally falls on the plant, not all of it is being completely used. Only a part of it is being used. So what fraction of light is being used compared to the entire light that is coming into is given by Q2, and we can estimate it if we know the incoming intensity of light. So this is incident PPFD for photosynthesis. PPFD is nothing but a photosynthetic photon flux density. Yeah, I think I'll include it. I haven't included the full form of it. It is photosynthetic photon flux density. And what is the incident photons available for photosynthesis, that is incident photons available for photosynthesis is what is given by I. Now, I is something that we can measure using the instrument. So we have that value. Now, what we need to know is phi PS2 and beta PS2. Now, phi PS2 is nothing but the dark adapted quantum yield of photosynthesis, photosystem 2. And beta PS2 is fraction of the absorbed light that is reaching the photosystem 2. Now, out of all of the light photons that is reaching the plant, some fraction is being used. In that, what fraction is being used by photosystem 2 alone is represented by this beta PS2. Now, phi PS2 is a term that is giving us the yield of dark adapted quantum yield of photosystem 2. It is nothing but when you keep this comes as a part of chlorophyll fluorescence. I will not be going into the theory of that part as for now. But dark adapted, when you say a leaf is dark adapted, it means that you're putting the leaf in a condition where it is not receiving light at all. And then after a particular time, you expose that leaf to a sudden beam of light. So what happens during that time is given by this dark adapted measurement. So what is the yield, the maximum, how with how efficiently the light can be absorbed by the photosystem 2 once it is dark adapted is what is being provided by this 5ps2. Now, like I said, 5ps2, we are not say we are not doing any chlorophyll fluorescence measurement. So 5ps2 can also be estimated as a function of this leaf temperature. So for in order to obtain this 5ps2 value, which is the maximum dark adapted quantum yield of photosynthesis 2, we can estimate it as a function of leaf temperature. Now we have already measured the leaf temperature. So if you input the leaf temperature, it can calculate 5ps2. Now beta PS2, according to the literatures, it is again we can estimate beta PS2 also, but it is constant over a wide range of temperature. Now we see that all of this is temperature dependent. But in case of beta PS2, it has been seen that at number of temperatures, if you estimate it for a number of temperatures, you see there is no much difference. So usually one constant is taken as beta PS2 in the absence of this chlorophyll fluorescence measurements. We are not doing any measurement to see how the chlorophyll molecules or the the plant that is, we are not doing any light based or chlorophyll fluorescence based experiments. So in the absence of that, we can use this as a constant, which is around 0.5 or something that is taken in literature. 5ps2, you can calculate it as a function of temperature. I we know because again that is being measured by this instrument, and leaf reflectance coefficient is also considered as a constant. 1 minus leaf reflectance is because this is equal to absorptance of absorption of the leaf or absorptance coefficient of the leaf. This is something like this alpha. So instead of that, we are writing 1 minus a leaf reflectance. Okay, so from this equation over here, for this equation over here, we were able to estimate the J value, which is the rate of electron transport from this non-rectangular hyperbolic equation. We saw what are the terms in this. We see Q2 is the fraction, a maximum fraction of incident photons that is available for electron transport. We see how Q2 is being estimated as a function of the 5ps2 as a function of a lot of factors like 5ps2, beta ps2, all which are light related. And then we also see that we have the convexity term for electron transport rate, which is again considered as a constant. But if all these constant can also be estimated, but as of now, we're going to consider as a constant. The convexity term is going to be constant over a wide range of, again, for a wide range of curves that has been calibrated or estimated. It is not very different. So we're going to take that also as a constant. Now, another thing we see here is EC and E naught. So this is the, how do we know what is the electrons that is available for carboxylation and electrons available for oxygenation. So we see that around 4.5 electrons are needed per carbon dioxide to regenerate ATP and NADP supply. So for one carbon dioxide molecule, there is around 4.5 electrons required to generate the energy. And during the photorespiration, around 5.25 electrons are required per half of half an oxygenation of to to release carbon dioxide. That during photorespiration, carbon dioxide is removed from the system. So for half a molecule of carbon dioxide, 5.25 electrons are used. So in order to make it for one full molecule of carbon dioxide, we multiply it with a 2 here. Now this EC value and E naught value, again, I'm taking it as 5.25 and 4.5. But then there in the literature, you can find that, both of them are taken as 4. So if you see electrons per carboxylation is taken as 4 and electrons per oxygenation is taken as 4. So during the oxygenation process, around 8 electrons are wasted to remove carbon dioxide, whereas during the carboxylation, 4 electrons are used to fix carbon dioxide. So again, this is an example of how wasteful the process is. Electrons are unnecessarily wasted for the regeneration of all this phosphoglycolate into PGA. So during that, whatever energy is used, whatever electrons that could have been used for fixing carbon dioxide is going for removing carbon dioxide in the photorespiration phase. So this is the meaning of the electrons per carboxylation and electrons per oxygenation. So you see in this RUBP regeneration limited phase, everything is related to electrons and light. Except for this parameter, which is a bit temperature dependent. Even this parameter is related to light, but since we don't have access to that data, that is why we measurement of that. That is why we are estimating it as a function of temperature. But again, this is something that you can get from this light response curve. But then we haven't measured the light response curve. So in that case, what do? We can only use these equations. And all of these equations are electron transport rate, light related and related to the AQ curve. So this is one part of the equation which is very much dependent not on the carbon dioxide concentration, but on light and how that light is helping in the electron transport. Okay, just a second. Does anyone have any doubt regarding this portion? If no, we'll continue, else you can ask. Okay, so I'll move on to the next part, which is the TPU limited. So we see here, we got the Rubisco limited photosynthetic rate, we got the RUBP limited photosynthetic rate. Now let's move to the TPU limited photosynthetic rate. Now, TPU limited photosynthetic rate is not very complicated in comparison to the all. We have one parameter called VTPU, which is the maximum rate at which triphosphate utilization is happening. This unit is not correct. I will correct it and put it. So again, just like VC max and J max, the maximum rate of please note this unit is not correct. This is not carbon dioxide. It is micromoles of triose phosphate or something like that. So it's not carbon dioxide. We'll correct it in the slides and post it later. So maximum TP, if you measure what is maximum TPU rate, and multiply it with 3, you will get what is the photosynthetic rate in that TPU limited phase. So we see we got all the three types of photosynthetic rate. Now, after finding this three types of photosynthetic rate, we are going to find which is the most minimum value of all the three rate of photosynthesis, and then subtract it from the rate of respiration, and then we'll get the net photosynthesis. Again, rate of respiration we can estimate. Suppose we don't have the AQ curve. Like I said, during the RUBP regeneration phase, we don't have an AQ curve. So we had to estimate the parameters. Similar way, RD is also estimated as a function of temperature. So we can estimate RD as a function of temperature, and we can estimate AC, AJ, AP minus the minimum value out of AC, AJ, and AP, which is the least value, minus the dark respiration from that value, and then we will get the net photosynthesis rate. So this is what the Farquhar-von Kammerer uh, model is based on, and it is strictly based on getting information or on the ACI curves. Although there are some set of parameters that we can obtain from the AQ curve, in the absence of an AQ curve, we have to measure an ACI curve, and it is only from that that we can make estimates of all of these parameters. So now I'll just share a quiz with you. You can answer that to just see how much of the content you have been able to grasp. So let me share this quiz with you. I hope the quiz is visible to all. If someone is not having access to it, please let me know. Please answer the question, and we can, and you can itself um, have an idea about how much you've understood from this portion, and if anything requires to be explained or to be gone in detail, we can discuss that during the rest of the class. So if you've attended the quiz and if you don't have any doubts or you don't want, is there's nothing to discuss, you can exit today's class. I think that will be for. Those of you who've attended the quiz can, if there's any doubt, you can ask. Otherwise, you can leave the session. And, is everyone planning to attend the quiz? Mayank, you can just attempt it. I will be posting the correct answers in the, I mean, I'll be sharing the results so you can verify against that. Else I'll be posting the video also, so if you can go through it.
Ma'am, okay, ma'am, but it is not possible because there is a lot of rush in work. and I'm standing here.
It's what you're saying is not clear. Can you?
So, that there is a ma'am, network issues also persist. Maybe
It's
therefore it
okay.
can.
It's okay. I'll do one thing. I'll be sharing the questions in the group, so you can go through the questions then. I've shared a QR code. I don't know if you can attend the quiz through you. If you could access it through the QR code. I've shared it.
Ma'am, both previous courses was attempted by me on that particular module learning website.
Okay, okay, okay,
Uh,
okay. It's
but
if you're not able to attend it, no problem. I'll post it somewhere.
okay, okay, ma'am.
Okay, okay,
Thank you, ma'am, for sending my
okay, okay, okay,
question.
okay. Thank you. Looks like everyone has attended the quiz, so I'll be ending the poll now. So yes, if anyone has any doubt, you can ask, or else we can end the class for today. Krishna and Mayank, do you have any doubts?
Yes, ma'am, I have some doubts, and because I am listening whole lecture, but as you know, my I
Oh,
will not.
okay, okay. There is a Google form or a Google form attached in the WhatsApp group. You can use that to, uh,
Convey
put
my
in your
queries
doubt.
to you.
Yeah, yeah, you can do that.
Thank you.
Krishna and Mayank, if you don't have any doubts, you can exit the session.
Thank you, ma'am.
Yeah, sure.